welcome to the first annual High TC Superconducting meeting. I'm Neil Ashcroft, representing a division of whatever it is now, and I would like first of all to introduce our distinguished guests from overseas who set this magnificent engine running. Dr. Müller from Switzerland. Dr. Tanaka from Japan. Dr. Paul Chu from Houston and from Foggy Bottom. Dr. Zhu from the People's Republic of China. And Dr. Batlog from USA/Austria. The chairman for this evening's session is Professor Brian Maple here. And I'm going to be very brief before handing over the microphone to him to get started. I just want to explain that if ever there was a post-deadline event, this is it. I want to express my extreme appreciation to Mr. James Spellos and his staff for being so accommodating in helping to arrange this extraordinary session. I think what we're seeing here is one of the most exciting developments in physics in decades, and I think it's a clear indication, once again, of the versatility of our subject. You only have to consider that in the last handful of years, we've had the integer and fractional quantum Hall effects, the heavy electron systems, quasi-crystals, the scanning tunneling microscope, and now high TC. It's utterly remarkable, and I think more is to come. I think that these remarkable discoveries exemplify the importance of investment in what I would call tabletop physics. Along with our colleagues in materials physics, preparation, characterization, synthesis, and so forth, the pace of discovery that we have seen recently can hardly be matched. Now, for tonight's pattern of events, the leading panel that you see here will give a brief description of their seminal discoveries, to be followed by the briefest of question periods, about 20 minutes or so. And then we will move into a pattern in which people will have essentially 5 minutes, grouped again in sections of 5 speakers to present their results, and at the end of each group, we will have a brief question session. Now, in order to facilitate the mechanics of this operation, we are going to ask that each group of 4 or 5 speakers, as designated in the sheet prepared by Professor Maple, come up to the podium here and be available to give their talks and then to ask the questions and then to depart and let the next group move up. I think this will expedite the proceedings considerably. Now, this event is a multimedia show, and for 2 reasons we are videotaping it. The first is, of course, for archival reasons. We're now moving into a new version of Physical Review, whose title I'm indebted to Jan Herbst for, and you will see it here now as our editor of Physical Review reveals it on the view graph. Can you take the cover sheet away? This event will be now the first volume, tape 1, of Physical Review V, the video version of the Physical Review. And in case of any of you have worries about precedents and so forth, you will now, or soon after this meeting, be able to purchase a tape, and instead of reaching onto your shelves for the appropriate issue of Letters, you can take down this videotape and point to your own publication. Now, but secondly, and more practically, we realize that we have a remote audience out there, and also some people are not able to be present here tonight. And so the whole proceedings will be taped, and for this reason, the mechanism and the mechanics that we've invented for tonight, I think, will assist very much in getting everything down on tape as much as possible. Now, for the formalities, we do ask you to keep to time. I think it's obvious why. And please heed Dr. Maple's requests. If he asks you to shut up, please shut up. We have to get on with it. A lot of people have got some incredibly exciting results to report, and we want to hear them all. The good news is that these short reports will last no more than 5 minutes. The bad news is that we have the room till 6 in the morning. So now, we recognize, of course, that not all of the statements that will be made tonight will necessarily go unchallenged, and you will want to ask questions. And there are microphones located strategically in the aisles here, and that's one of the reasons why we want them clear. And we ask you, please, if you have a question, to move discreetly and quietly up to the nearest microphone during the block of talks that is going on to ask your question. And I would ask you, please, to make it a question. That is to say, no filibustering, no polemics, no perorations, just a straight, clear question, please. And the clearer and the shorter and the briefer it is, the more we will get done. So that leaves, of course, our external audience. And we know, of course, that the external audience out there on the foyer and so forth will also have questions. To handle that problem, the best we can suggest is that you please, if you have a question, write it down on a card and bring it to the door outside the symposium head here, and during the evening, not necessarily during that particular point, we will try and get your question answered. Finally, we recognize that many of you had perhaps an early dinner tonight. And as I said, we have the room till 6 in the morning. And you may need a little blood sugar fix here or there. The hotel is setting up a place outside here where you can obtain drinks. And I'm also told that downstairs, the snack bar will be open until about half midnight. Finally, my final remark before handing over to Brian is a very important one. I doubt that this discovery could possibly have been made without people paying attention to the crucial properties of materials, and I mean materials with a capital M. And as you may know, there has been a national study going on the role of materials in this country, and indeed that the interim report of that study was to have been given tonight. For very evident reasons, we moved it to tomorrow night. Now, some of you may now be more than unusually concerned about the contents of that report because of the events that will be taking place tonight. And I would like to urge you to attend the interim report tomorrow night and express your views about the importance of the role of materials physics and condensed matter physics in our country. So that will be going on tomorrow night at 7:30. So those are the end of my remarks, and the only other thing I should say on behalf of the APS is if you haven't registered, please register. We need your support. Thank you very much.
See, we have a few announcements to make here at the beginning. First, Myron Strongen, is going to make a few remarks about the physical review and how it's going to handle these papers.
It's a great pleasure to be here at this great event. I must say it's my luck that I was on the scene when Gene Wells took his vacation and we had to fill his sabbatical, and we had to fill in for him. Now let me tell you how we've handled this so far and what we intend to do in the future. When the initial papers came in, the original Paul Chu paper and the Bell Labs paper, it was obvious that we had to get these out very quickly. So the usual refereeing system was modified a little bit. We suggested in both cases that the groups should send out preprints to 5 referees, potential referees, and then we would call these people and get opinions on these papers. And this was done, and that's how we got in the original papers fairly rapidly. The next batch, some papers started coming in then. They were put in the system in the usual way. And eventually 3 theory papers came in. At this point, we realized that not only did we have to get them in very rapidly, but we had to be very consistent in the way that the papers were handled. And the intent was that everybody deserved to get their stuff in publication, and we had to be consistent. So these papers were then refereed in batches. The 3 papers were sent to 2 referees, and they basically accepted these for publication in PhysRev letters. Finally, when the great 90-degree discovery happened, again, by mutual agreement, the referee was chosen, and this was handled, again, very rapidly. And all the papers to date have been refereed. Now, during this time, I would say till about the beginning, maybe until a few weeks ago, there were about 30 papers in the channel. Now, at the present time, I've been told in Tuesday morning there were 75 papers. As of Wednesday, as of tonight, there are 77 papers that have been submitted to PhysRev letters and 12 to Rapids. So if we handle this in the usual way, I think everybody could appreciate it. Would overload the system completely, the usual refereeing system, and there'd be no consistency in what got published. Now, luckily, a couple of weeks ago, I have asked 5 people. They're being kept anonymous for obvious reasons, but these people will serve as a panel and hopefully referee these papers until they get tired. As of today, the panel has received 50 papers. Each member of the panel gets all the papers, and we've tried to make one person on this panel the person who would submit a written report on the papers. So this is how it will be handled in the future until these people get tired. An editorial is coming out in the March 23rd issue of PhysRev Letters, and I think the April 1st issue of Rapids. And these people will then make the decision on whether the paper should not be published, whether it should be in PhysRev Letters, whether it should be in Rapids, whether it should be a brief report or a full-fledged article. So we hope everybody's understanding. The intent is to try to get everything out and get them in the journals as quickly as possible. Thank you.
Thank you, Myron. We also have another brief announcement from Cy Moss.
This works? Yeah, good. I just wanted to make an announcement relating to the Materials Physics Topical Group of the APS. As many of you know, we run focus sessions at this March meeting, and they've been quite successful, I think. And it's clear that these are banner days for materials scientists and materials researchers. And so we are soliciting requests for suggestions for focus sessions at the 1988 March meeting, and those suggestions on materials aspects of superconductors, including preparation methods, phase relations, structure and defects, and so on, other things dear to the hearts of materials researchers, and would like these suggestions sent in to me at the University of Houston by May 15th. That seems early, but it starts the process going wherein we select chairman for the focus sessions and begin our process of getting invited talks and so on and so forth. So we earnestly solicit your recommendations. Thank you.
Thank you, Cy. Before we get started, let me just say that it's unfortunate that the late Professor Bernd T. Matthias cannot be with us tonight on this historic occasion. Bernd was one of the pioneers in the field of superconducting materials who had really a tremendous impact, a major impact on its development. He was responsible for getting many of the people on this program and in this room involved in this subject, that of superconducting materials, including myself. Most important, he was a friend, and he would have loved to have been here tonight.
Can you help me to get...
So let's begin. The first talk on the panel, the talks will be 12 minutes, and I'll set the timer to indicate the time after 10 minutes. That will give you 2 minutes to finish up. The first talk will be given by Dr. Müller from IBM Zurich. The title of the talk is A Road to High TC Superconductivity, Experiments with Alkaline Earth Substituted Lanthanum Copper Oxide. Dr. Müller.
Well, I think, according to the schedule, my talk is now over. Yeah, I have entitled it A Road Towards High Temperature Superconductivity, which George Bednarz and myself think we have found. There may be other roads to achieve that. Now, what has been achieved? I have plotted here transition temperature versus the years where they have been achieved, starting from the discovery in 1911. And you can see from that graph that if you would extrapolate more or less linearly as a function of time, you would expect that by 1919 you would have reached about 30 degree Kelvin. Instead of that, already by the end of last year, one had exceeded this extrapolation by quite a bit, and by now, here I have plotted the confirmed results by the group of Professor Chu is well toward the 100 degree Kelvin. Now, the first observation in the new system dates back in January 27, when we saw the onset in the lanthanum barium copper oxide mixture, and by optimizing the substitution of the lanthanum by the barium, we were in April up in the 35 degree Kelvin range, and I show you the data which we submitted at that time. So essentially the whole search extended over about 2.5 years. It was strictly a two-man project, not even a technician was involved, it was George Bednarz and myself. And you see here that the resistivity as a function of temperature decreases metal-like, and then has a tendency to localize, and certainly you get the onset. And for example, for this sample, we couldn't measure, at least with our equipment anymore, any resistivity. Now, how did we find this material? Well, we had a concept for high TC superconductivity. Namely, I had come to the conclusion that one should radically abandon intermetallic compounds. There had been many groups who had tried to improve the the TC in this area, but do a search in metallic oxides. What was the rationale of doing that? Well, in 1973 at San Diego, they found a TC of 13.7 degree Kelvin in the lithium titanium spinel, and 2 years later at DuPont, Slide and co-worker found in the barium lead bismuth oxide a comparable high TC. Now, working in this area, both the group of Dr. Batlock here and the group of Dr. Tanaka found that the carrier concentration was of the order of 2 to 4 times 10 to the 21, which is about an order of magnitude less than what you have in a normal metal. And this was remarkable because this carrier concentration multiplied by the electron-photon interaction is essential for, in a normal BCS superconductor. The formula stands here. So that means that this electron-photon interaction had to be very large. And one could expect if one would try some other oxide, one may do better than that. So this was part of the concept. The other part of the concept was to restrict our search strictly to metallic oxides containing nickel and copper only in octahedral coordination. Why? Because they have partially occupied d orbitals which point toward the oxygen ligands. And therefore, this was our view. One would have a large interaction between the metal and the ligand. You see here the octahedron and a copper inside. And if you have a 3-valent copper, you have this z-square orbital occupied ones and this x-square minus y-square orbital also occupied ones. And they are degenerate in energy. If you have a 2-valent copper, then the further electron goes in this orbital here, and you get an elongated octahedron. This is expression of the Jahn-Teller effect. Now, I would just say here, it may be important in theory to consider, especially also in the new compounds, the degeneracy between these two orbitals, and not make a theory only for a single band from x-square minus y orbitals. For instance, Don Lee, in a very recent theory, has done that, and he will talk about that later on in this session. Now, another thing is that what is the interaction? How does the oxygen move? Well, you have basically two modes, a Bressing mode and a Jahn-Teller mode. The Bressing mode is shown as here. It changes the volume, and the Bressing mode is very attractive if you have, say, bismuth or lead, like in the bismuth-lead perovskite, because the bismuth and the lead tend to disproportionate. So this is a disproportionating mode in a way. On the other hand, here is the Jahn-Teller mode. You cannot distinguish in the XY plane the motion of the oxygens between the Jahn-Teller and the Bressing mode. It's only the out-of-plane motion of the oxygens which is different. Namely here, the red arrows show 180 degrees out of phase, and it's not a matter of so much of the amplitude, but of the phase. And to my understanding, there has not been experiments till now to distinguish between these two modes. This mode here preserves the volume of your octahedron, and this may be important because the copper ions in general, as far as I know, do not disproportionate. Now, the structure which we found is this potassium nickel fluoride 4. It's a layer structure, but this structure is tetragonal, whereas the one we have is slightly orthorhombic. What you have is sheets of copper oxygen 6 octahedra, and in between you have layers of lanthanum oxide. And these octahedra, they are now not in a plane, but they are slightly tilted along 1, 1, O directions if you don't substitute the lanthanum by, say, barium or strontium by alkaline metal ion. So without substitution, it's orthorhombic, and when you substitute, it gets tetragonal, as exemplified here by this X-ray data as a function of the barium content. So it's split here, and smoothly you see only one line. Here it's tetragonal, and it's around here at this concentration where you have the optimum transition temperature observed in these layer compounds. And I showed you our data for the orthorhombic case, case in between number 2 and 3 for optimum transition temperature in these layer compounds. So without, or barely without barium, you have the following thing. The resistivity as a function of temperature first decreases linearly, and then it strongly localizes. And the resistivity alone may be typical of something which is, has the behavior of a semiconductor, but the susceptibility, which is plotted here, is almost temperature independent. Pauli-like. So the statistics is still the Fermi-Dirac statistics, despite that the motions become slower. This has been termed a Fermi-glass behavior by Anderson. 2 minutes only. Oh. Now, in sample number 2, the onset here is somewhere around 27, and sample number 3, the resistivity onset is higher up, and the diamagnetism was it was becoming diamagnetic here at a lower temperature than here, so it was a systematic increase in TC, and we thought we have really, because it's becoming diamagnetic, superconductivity. Now, when we were asking ourselves, we had submitted this paper. One Monday morning, Dr. Takashige, who is from Japan, came to our laboratory and was quite excited because his wife has read over the Sunday the international edition of the Asahi Shimbun journal, and he found this, which essentially was saying that in Tokyo they had confirmed our results. We were very pleased with that. So now I'm going to just flash at you 3 view graphs before quitting. One thing is that in these compounds, in part, you have flux trapping and some superconductive glass state where you have, if you field cool it, it's reversible. If you zero field cool it, you have irreversible states. This is indicative of a superconductive state. Those who are interested may find further information in this week's physical review letter. Another thing what I wanted to say is the structure of the new compound, which has been determined in IBM Yorktown and IBM Almaden. You have essentially now a perovskite, a lattice, where you have barium, yttrium, barium, and this also shows up in transmission electron micrographs. In some of the layers, which I have not time to say, you have oxygen vacancies. And if you are interested in applications, then you may look at this result, which is, has been done at IBM Yorktown Heights over last weekend. It shows you the resistivity now over of a 400 nanometer thick film, which becomes superconducting here at this temperature, and because it's a film, is proof that some technical applications are possible. And with this, I thank you for your attention.
very much. We'll move on now to the second contribution, high TC superconducting copper oxides, given by Professor Tanaka, University of Tokyo.
Thank you. Okay. Oh, thank you. I would like to talk about the result of studies of our group on high TC superconductors, which have been performed in these several months. First, I will show you a list of the materials of which we have studied in these 10 years. We tentatively classify the materials into 3 groups. Class 0 means barium, lead, bismuth O3, which is known as low carrier concentration superconductor and seems to be the prototype superconductor of the present high TC superconductors. The second, a series of materials of lanthanum barium to kappa O4. The class 2 is lanthanide barium kappa oxide, which are very high critical temperature beyond 90 degrees Kelvin. In order to investigate new superconducting materials, the identification of the superconducting phase is the most important. To identify the superconducting phase, the 4 conditions must be satisfied, as is shown in the view graph. Crystal structure, Meissner effect, resistivity drops sharply, and the reproducibility of experimental results must be obtained. From November to early December of last year, we concentrated our effort in identification of the superconducting phase in lanthanum barium kappa oxide, which was first suggested as a high TC superconductor by Dr. Bednoz and Müller. We succeeded to identify the superconducting phase and it is lanthanum barium 2 kappa O4, having K2NiF4 type crystal structure. We succeeded to make samples of single phase of this type, and the temperature dependence of diamagnetic susceptibility and resistivity indicated that this material is a bulk superconductor and the critical temperature is about 30 degrees in Kelvin. We believe that these data were the most clear evidence of existence of high TC bulk superconductor beyond 30 degrees Kelvin at that time. Furthermore, we replaced barium to strontium and calcium and found that lanthanum strontium to kappa O4 is a very good superconductor, TC of which reaches up to 38 degrees Kelvin. Furthermore, we investigate the physical properties of these K2NiF4 type superconductors of 40 degrees Kelvin. We think that these properties are very important since the K2NiF4 type structure is rather simple and it must be easier to understand the mechanism of high temperature superconductivity. We used high quality samples. High quality means a large Meissner effect and very sharp drop of resistivity. Transition range is less than 1 degrees Kelvin, as is shown in this graph. Time is not enough, so I only show you the result of our experiments. We measured mainly the we measure mainly the dependence of many physical quantities on the concentration of barium or strontium. Resistivity, Hall effect, carrier concentration increase with increasing doping. Zeebeck effect, next. plasma reflection. Let's see. Omega P is almost 1.5 micron. Paramagnetic susceptibility. You see, this is x equals 0. The paramagnetic susceptibility increasing the with increasing the doping. And heat capacities. These data indicates a large density of states. Yes. This is ransom calcium kappa 4. The next one is this is ransom strontium kappa 4. And gamma BCS is quite large. And effect of high magnetic field. Temperature dependence of the conductivity and the high static magnetic field. HC2 estimated to be 60 Tesla. Okay, 60 Tesla. Okay. Summarizing the data, finally we make a tentative list of normal physical parameters and superconducting parameters. Next one. Such like that. Furthermore, we replace ransom partly by rare earth elements. These results indicate that that the depression of critical temperature on the total temperature depend on the concentration, total spin of rare earth element. You see, this gadolinium is lowest critical temperature. So this means that this suggests the spin exchange interaction with the conduction electron is effective on the critical temperature. Then I will talk about the result of yttrium barium kappa oxide, which was first made by Professor Chu. In Japan, however, Professor Hikami of University of Tokyo made yttrium barium kappa oxide quite independently and observed high TC of 85 degrees Kelvin in the middle of February of this year. We succeeded also to make yttrium barium kappa oxide of almost single phase. Almost you can see in this graph, the Meissner effect reaches up to 50%, and the shielding effect signal reaches up to 150%. The rise of diamagnetic susceptibility, the diamagnetic signal is quite sharp at 94 degree Kelvin. The resistivity also drops fairly sharply at 94 degrees Kelvin. H1 is almost 100 L at 5 degrees in Kelvin. Outer crystal structure, the pattern of X-ray spectra quite resembles that of lantern-2 strontium kappa 2O6. And then first we thought that it is S3B07 type. But later we found a line of a triple layer period of C. Then now we think that the crystal structure consists of triple layers. A model of this type of perovskite oxide was proposed by French chemist group, as shown in this graph. But the position of the oxygen ions cannot be determined by X-ray diffraction method. The correct identification of superconducting phase is a future problem. Now we proceed to new materials which were found by Japanese groups. We replace yttrium by other ransomized elements such as yttrium, tritium, erbium, holmium, and diploshub, and found that all of them showed high TC of 90 degree Kelvin. They have the same X-ray pattern as in yttrium, barium, copper oxide. I will show you some of the data as follows. Yttrium, erbium, diploshub, and so on. It is very interesting. They have a magnetism at temperatures beyond critical temperature. So we can say that they are new type of high TC superconductors, and at the same time, they are new type of magnetic superconductors. It is surprising that the magnetic moments of these lanthanoid elements do not affect the superconductivity at all. This fact may be related to the layer structure of these crystals. And this may provide a basis to clear out the electronic structure of these high TC superconducting materials, as well as the mechanism of superconductivity. Thank you.
Thank you very much. The next panelist is Professor Paul Chu, superconductivity above 100 degrees.
It's a little bit tricky, huh?
See, the next panelist is Professor Paul Chu, superconductivity above 100 degrees.
Thank you. Thank you. I think it's okay. Yeah, it's okay. I think I would take this opportunity to first thank Alex Müller, George Batnos for bringing across all this problem. And then I would also like to thank Bernd Matthias, of course, he's not here now, and also Art Slate, who brought me to, gave me the interest, made me interested in the superconducting oxides. And also for John Bardeen, Marvin Cohen, Ted Jabor, and C.Y. Huang for their belief in non-conventional superconducting mechanism, and also Art Freeman, for his enthusiasm, constant enthusiasm, and also for his valuable information concerning band structure calculation. Of course, the support from National Science Foundation and NASA, and also University of Houston are greatly appreciated, especially for those colleagues at NSF who are making the so-called flexi-time schedule of the federal government more flexible to accommodate my erratic working schedule between Houston and Washington, D.C. And last but not the least are my colleagues and students for their many sleepless nights and also hard working. Because of time, I just show this, mainly the group at University of Houston and University of Alabama at Huntsville, headed by Professor Wu, and also Lockheed Research Center, C.Y. Huang, and also Los Alamos National Laboratory, Chern Gibble, and Joe Thompson. And also particularly, I appreciate the collaboration with geophysicists from the Geophysical Lab, Dave Mount, Bob Hazen, and other people. I think the whole thing started, as I mentioned previously, because after we recognized the existence of the Swiss results, we decided to reproduce the result. Indeed, it was superconducting at around 35 degrees. So we decided to see what's happening there. So we decided to apply pressure, and also by changing the chemicals substitutions, we found that the pressure effect was extremely unusually large. And then immediately we decided to simulate the pressure effect by substituting a barium with strontium, which has smaller radius, atomic radius. Immediately the TC went up without the application of pressure. We thought just by squeezing it, the TC would go up to much, much higher. But unfortunately, when we replace barium with calcium, which has even smaller atomic radius, the TC goes down. So this tells us there exists an optimum interatomic separation for high TC. And then the other hint, by that time, by the beginning of this year or the end of December, we accumulated quite a bit of data. We found out that the TC usually, the onset TC goes down when you make the material purer in the so-called layer structure, and also when the width of the transition goes down. So this tells us something. And then there's also, by that time, we have observed lots of indication of superconductivity as at temperature higher than 70 degrees, but only in those material without the layer structure as the main phase. Let me just show you this curve, original curve measure on November the 25th. You see the resistance drops all the way starting from 70 degrees to 50 degrees, and this was mentioned in our first paper. And then we continue on. We decided in order to look for higher TC material, we have to go into... I'm sorry. We decided for TC higher than 70 degrees, we should go into compounds with structure different from K2NiF4. In fact, here I can also show you another compound which shows magnetic measurement starting 100 degrees. I purposely turned it upside down. And going like this starting from 100 degrees. But unfortunately, this signal disappears after a day or so. So then we decided to look for new compound. Unfortunately, on January the 28th, and this was observed. And Professor Woods tried to impress people. In fact, he only measured it down to 77 degrees by using the liquid nitrogen duo. As you can see, resistance really goes down. And immediately following that, we improved the temperature at the samples slightly. And right now, the resistivity at that time, a few days later, we got the onset at 98 degrees and goes down to 0 at 94 degrees for the yttrium barium copper oxide. As you know, at that time, by this time, we also went to measure the critical field. The Meissner effect, in fact, with the Los Alamos group and also Lucky, C.Y. Huang and our group working together, and that was the first time measuring the DC Meissner effect, confirming that this is indeed a superconducting transition. And also from our preliminary study, it shows that this structure is different from the characteristic of this material is different from the so-called layer structure. And so now, unfortunately, at that time, our sample has two phases. One is black and the other is green. And then by the end of February and also the beginning of March, working together with the geophysical laboratory, especially Bob Hazen and Dave Mao, who have extensive experience handling dirty samples like rocks. So they separated and identified the phase. The superconducting phase indeed was the black phase, has a composition expressed here with x less than 3. And it has a tetragonal symmetry. And the non-superconducting green phase has this kind of formula with the orthorhombic symmetry. And let me just show you, because Dr. Hazen is going to describe the structure later, let me just show you briefly. This is his wave graph here. As you can see, you have layers something here. I'll come back to this structure later when we discuss the occurrence of superconductivity here. Now, with all that, we decided to find out what is the active components for superconductivity above 90 degrees in this class of material. And so we decided to replace all these elements, A elements, by all this whole bunch of elements. And we found that basically the TC is almost constant. And here's the table of all the TC. The TC basically, TC0, the onset temperature is between 91 to 98 degrees. And then the resistance goes to 0 between 70 to 94 degrees. I believe the 70 degrees can be improved later. And then also look at the linear deviation. The deviation from linear temperature dependence of resistance starts as high as 160 degrees. And if you want to define that as the onset temperature, certainly you may. And then we also found all this material becoming superconducting. And then when we measure the diamagnetic shielding, AC shielding, it goes from 97 to 100% now with all this material. So from this study, we realized that superconductivity is independent of A atoms. And then when we look at the structure, they are quite interesting because they have the layer structure. Actually, it has CO2, that kind of, this kind of structure. I think it's what I would like to show this, very interesting, because if you look at here, I did not put down the 6 plus x. The x I haven't put it in. And basically, if we only look at x without only 6 without the x, and that's the structure. And the most interesting part is this. when we look into the lanthanum, barium 2, copper 04, the layer structure, and this is the structure. And you have layers of copper and CO2, copper oxygen 2 layers going like this, here and here. And they're separated here. According to band structure calculation of Lenny Mattis and also R. Freeman, they're not coupled. And here we have 3 here, okay? Well, and then 3 units up here. And then when we change this 8 elements, it has no effect on superconductivity. Perhaps now we can consider that superconductivity actually is confined in this region. Okay. And the interesting part is this. If you look into that, in the layer compound, we have 1 layers. They're not coupled. And then in the new compounds, it has 3 layers. One layer has 30 degrees, and 3 layers has 90 degrees approximately. Is this accidental or not? We don't know. But certainly those 3 layers are coupled through the barium. And whether that's true or not, it has to be determined. But so based on this result, we think maybe we need bigger layer assembly and to get to higher temperature. And I would like to emphasize at this point, there are indications of superconductivity at 120, 150, 240. In fact, I should mention the 240 drops of resistivity at that temperature, not only observed by us, but also observed by by the Berkeley group, Marvin Cohen and Alex Zeto's group. Do I still have time? Okay. So now, with all that results, what are the major ingredients in the superconductivity of this class of material? It appears to us right now all these structures have some defects, and therefore there must be local deformations associated with defects in here, so it must be important. And the second thing is all that assembly of layers over there, it retains some kind of quasi-2-dimensional characteristic, because when you change the 8 elements, you don't change the superconductivity. So it indicates that perhaps those 3 layers do not really couple strongly. It retains some 2-dimensional characteristics. And also, in the potassium nickel fluoride structure, where the barium and the 8 atoms are not really ordered, they are disorderly arranged. But here they are ordering, okay, in range in the 90 degrees one. So with all this, it appears to us, as already Dr. Müller already pointed out, perhaps in this class of material, we need some new kind of superconducting mechanism, and mainly of electronic in nature. So then what is it? It appears to us it's due to the coupling of electrons through the virtual exchange of excitons. And the excitons, if we look into there may be generally grouped into 2 types. One is the excitons and charge carriers are in different spatial regions. In order to accomplish that, we're talking about interfaces. Interfaces can exist both in a compound system with 2 different structure phases, or even in the same phase. Okay? If we look at the layer structure, we may accomplish that kind of situation. And this kind of model has been previously proposed by Bardeen and co-workers, and also Ginsberg, and also CST, my colleague at the University of Houston. Now, what would happen in the other case, where the excitons and charge carriers in the spatial regions, in the same spatial regions? Okay? In that case, then we can make use of the so-called plasmons mechanism, which has been proposed by Crescent of Lawrence Rady, LBL, and also John Ruwald of Virginia University. According to their models, 2-dimensional plasmons, acoustic plasmons, can help us to achieve higher TC. But then what about the charge? Because when you look into this layer, the coppers charge are transferring between different states, and therefore Chandra Varma proposed a charge transfer fluctuation situation where you can get an enhancement in superconducting interaction. And then the other type is perhaps when you look at all this material, they all have some magnetic origin in it. The subtle, as we observed previously, the material lanthanum copper barium oxide, you can make it into insulator, you can make it into superconducting, you can also make it into magnetic situation or magnetic compound. So here we are talking about a possibility of spin fluctuation associated with the copper 2+ ions, and that can enhance superconductivity and get a D-pairing, just like people proposed in the heavy fermion situation. And then the other model is resonating valence bound state proposed by Phil Anderson, and it appears to us at this moment, and there's no experiments which can distinguish one from the other at this moment or rule out any of this, and I think they all deserve some attention. Now, one final conclusion. Can we get TCE higher And I believe we will be able to get higher TC. And let me just show you one of the curve here, which is just an indication of superconductivity. In fact, we have cited this kind of drop in resistivity more than 15 times now. And we hope with the hard work of everyone, we can stabilize that phase. Thank you.
Thank you very much, Paul. The next talk is by Professor Zhao from Beijing, superconductivity above liquid nitrogen temperatures in barium yttrium copper oxides.